Welcome to today's paper reading. Today's paper is titled, Training Language Models to Self-Correct via Reinforcement Learning. This paper was published on the AR14 preprint by Aviral, Kumar, and colleagues from Google DeepMind. The abstract presents the self-correction results before and after fine-tuning on datasets STAR and SFT. It highlights that while the change in performance, delta, T1, T2, is substantially higher for pair SFT compared to the base model, the benefit of self-correction is minimal, with only a 1.8% gain. This gain is comparable to findings from Chu et al., 2024. The study of delta IC and delta CI reveals that SFT primarily reduces the number of correct problems that are incorrectly changed in the second attempt, without significantly increasing the correction of incorrect first attempts. This aligns with previous research on intrinsic self-correction, which found negligible or negative delta, T1, T2, values. Additionally, training on STAR does not reduce delta CI, suggesting that the STAR policy lacks a clear understanding of when to modify responses. The inclusion of correct-to-correct data in an extended version of SFT helps STAR but only results in a 0.4% change in delta, T1, T2, while for SFT, it biases the model against changing its answer. Figure 1 illustrates the performance of SCORE in self-correction tasks. On the left, it shows that SCORE achieves state-of-the-art self-correction performance on the math dataset. This demonstrates the effectiveness of SCORE in improving the self-correction abilities of large language models. On the right, the figure highlights the inference time scaling of SCORE, indicating that spending samples on sequential self-correction is more effective than only on parallel direct samples. This finding suggests a more compute-efficient strategy for inference time scaling, where sequential self-correction can yield better results with the same computational resources. Overall, Figure 1 underscores the advancements made by SCORE in enhancing self-correction capabilities and optimizing computational efficiency. Figure 2 presents two illustrative examples of SCORE's self-correction capabilities. The upper example showcases SCORE's ability to identify and rectify an arithmetic error made in the first turn. The lower example demonstrates the model's proficiency in correcting a reasoning error. These examples highlight SCORE's multi-turn self-correction process, where the model iteratively refines its responses to achieve more accurate solutions. Figure 3 illustrates the self-correction problem setting. The SCORE framework trains a model not only to produce the best possible response initially but to aim for the best final response after potentially multiple attempts. In the second turn, additional input is provided, such as an instruction for the model to correct itself or model-generated content. The goal is to maximize the correctness reward obtained from the verifier after multiple turns, emphasizing the importance of self-correction in improving final response quality. Table 1 presents the self-correction performance metrics after training on datasets STAR and SFT. The key findings indicate that the improvement gap between the first and second attempts, delta, T1, T2, is either negative or small. Additionally, both training approaches show a high rate of correct responses being modified to incorrect, delta CI, 1, 2, and a low rate of incorrect responses being corrected, delta IC, 1, 2. These results highlight the challenges in achieving effective self-correction through these methods. Figure 4 illustrates the edit distance between the first and second attempt responses from fine-tuned models, including our approach, SCORE, and the base model. The data shows that while training on self-generated error correction traces primarily teaches the model to avoid making major edits, the SFT model learns to make some edits, but remains quite conservative in its approach. Figure 5 illustrates the self-correction performance on two types of first-attempt responses, fixed and self-generated. The fixed responses are sampled from the initial model, while the self-generated responses are created by the learner itself. During training, the correction rate on fixed responses shows an increase for both training and validation problems. However, the correction rate significantly degrades on self-generated responses. This observation suggests that training on a fixed offline dataset of correction traces faces challenges due to distribution shift. Figure 6 illustrates the issue of behavior collapse and standard multi-turn reinforcement learning, RL, for training self-correction. This phenomenon is characterized by the model's tendency to not change its response, leading to a lack of self-correction ability. The results indicate that an explicit approach to avoid this collapse is necessary, such as the stage I in SCORE. This stage is designed to alleviate the coupling of responses at different attempts, thereby increasing exploration and improving the final performance of the model. Figure 7 provides an overview of the SCORE approach, which involves a two-stage training process. In stage I, the model is trained to produce high-reward responses in the second attempt while mimicking the base model's initial response. This stage aims to decouple the behavior across the two attempts. Stage 2 then focuses on jointly optimizing both attempts, using a shaped reward to encourage the discovery of a self-correction strategy rather than simply producing the best first response followed by minor edits. Table 2 presents the performance of SCORE on math, demonstrating its superior accuracy at both first, ACC, at T1, and second, ACC, at T2 attempts. Notably, SCORE provides the most positive self-correction performance delta, T1, T2, indicating a significant improvement over the base model and other approaches. Additionally, SCORE outperforms in delta IC, T1, T2, and delta CI, T1, T2, further highlighting its effectiveness in self-correction tasks. Table 3 presents the performance of SCORE on the human eval dataset, highlighting its superior self-correction capabilities. SCORE achieves the highest self-correction accuracy at the second attempt, accuracy at T2, with 64.6%, a significant improvement over other methods. The intrinsic self-correction gain, delta, T1, T2, is 12.2%, which is notably higher than the base model. Additionally, SCORE outperforms in offline correction tasks on MBPPR, reaching 60.6%, demonstrating its effectiveness in both self-correction and offline repair scenarios. Table 4 presents the results of ablation studies designed to assess the impact of different components in the SCORE framework. The data reveals that while single-turn training effectively enhances the model's first attempt accuracy, it results in a decline in the second attempt. Notably, the enhancements in performance when either stage I or reward shaping is omitted are quite modest, as indicated by the small differences in accuracy across the two attempts. Furthermore, the substitution of star for reinforce in stage 2 generally results in diminished performance, even when initiated from a proficient stage I checkpoint. The introduction of this paper highlights several key contributions in the field of training large language models, LLMs, to self-correct using reinforcement learning. One of the primary focuses is on self-debugging capabilities within LLMs, as demonstrated by Chen et al. In 2023. Additionally, the paper references Aviral et al. 2024a, who explore the use of reinforcement learning to enhance the reasoning abilities of LLMs. Another significant contribution is the iterative refinement with self-feedback, as proposed by Madan et al. In 2023. The paper also discusses various evaluation methods, including the use of the math dataset for measuring mathematical problem-solving skills, Agent Bench for evaluating LLMs as agents, and reflection for enabling autonomous agents with dynamic memory and self-reflection. In this section, we explore the performance of various models and self-correcting over multiple attempts. The base Gemini 1.5 Flash model shows noisy performance without surpassing the first attempt. ParisFT does not improve beyond the second attempt. In contrast, SCORE shows a slight increase in performance past 2 turns, though it plateaus due to rapid shifts in response distribution. We also examine the impact of the discount factor gamma in the reward function. Using only instantaneous rewards, gamma equals 0, in our policy gradient objective, we find that introducing gamma 0 does not improve self-correction behavior. Finally, we detail the hyperparameters used for training SCORE and provide examples of prompts and self-correction instructions for math and MBPP tasks. Figure 8 illustrates the performance of 3 models, the base model, ParisFT, and SCORE, across 10 self-correction attempts on the math dataset. The base model's performance is erratic and never exceeds its first attempt. ParisFT, trained for 2 attempts, fails to improve after the second iteration. In contrast, SCORE demonstrates a slight increase in performance beyond 2 attempts, though it eventually plateaus, likely due to rapid shifts in response distribution with additional revisions. This figure highlights the challenges and potential of iterative self-correction in improving model performance. Figure 9 illustrates the impact of the discount factor gamma on standard multi-turn reinforcement learning (RL) training. The study examines whether incorporating a discount factor greater than 0, specifically gamma equals 0.8, in conjunction with reward shaping, alpha equals 1.0, can improve self-correction in RL models. The results show that despite these adjustments, multi-turn RL training still experiences the same non-correcting behavior collapse as observed in the standard multi-turn RL approach. Table 5 presents the hyperparameters used for training the SCORE model on two datasets, Math and MBPP. The table details the base models, optimizer settings, learning rates, training steps, batch sizes, and other relevant parameters for both Gemini 1.5 Flash and Gemini 1.0 Pro models. These hyperparameters are crucial for understanding the configuration of the SCORE model during its training process on these datasets. In the experiments, SCORE demonstrated its ability to refine its own responses in several ways. It can rewrite entire solutions when necessary, or it can reproduce the correct parts of the solution while revising the incorrect ones. Notably, SCORE is particularly adept at correcting its computational mistakes and shows a tendency to include more steps in certain computations to increase the likelihood of producing a correct answer. Additionally, the model learns to occasionally self-correct within a single turn, as observed in examples like Math Example 4. The examples provided in Appendix E, such as Human Eval Example 1 and Human Eval Example 2, illustrate these capabilities in detail. In the analysis of related work, a critical calculation was performed to determine the number of representatives, denoted as X. The calculation yielded X equals 2106 divided by 169, resulting in 12.47. Given the impracticality of fractional representatives, the decision was made to round up to the nearest whole number, which is 13. This approach ensures that all voices are fully represented, avoiding any potential underrepresentation and aligning with the principles of democratic representation. In this study, the final answer derived is 13. The author expresses hope that this answer is correct. Additionally, the SCORE Turn 2 solution involves calculating the ratio of 7th grade students to 8th grade students, which is found to be 520/650, or 4/5. This ratio is crucial for ensuring fair representation on the student council, where the number of 7th grade representatives should be proportional to the number of 8th grade representatives to maintain equity. Thank you for watching.